The animation you are seeing is a vastly exaggerated version of a well-known effect caused by gravitational waves. A gravitational wave will cause a correlated periodic oscillation in the apparent locations and relative separations of a set of distant stars. The effect is largest for widely separated stars, and it of course depends on both the gravitational wave propagation direction and on the polarization of the wave. Unfortunately, when one estimates the actual size of the effect, it is much more like that shown here, extremely small and hard to detect. Previous studies that have looked for this effect have thus focused attention on large-scale photometric survey data, such as that provided by Gaia or the future Roman Space Telescope. The single-star astrometric precision of these instruments is not sufficient to see the tiny gravitational wave signal. However, using very large numbers of stars, it is possible to obtain deeper strain sensitivity. Unfortunately, in the frequency band from about 10 nanohertz to about 1 microhertz, such approaches still do not achieve the target strains required to see the most interesting expected sources. The work I will speak about in my parallel talk explores a different corner of the optimization trade space for measurements of this effect. We asked a simple question: can one instead aim to make extreme precision measurements of a small number of stars? If you come to my talk, you'll hear more about how we identified a promising class of stars that one could make astrometric measurements of to achieve this approach: hot, distant white dwarfs. I'll also tell you about how one might go about obtaining the extreme astrometric precision required by sketching out some parameters for a future space-based stellar interferometry mission. This would rely on separate formation-flown spacecraft with baselines on the order of 100 kilometers, containing light collectors on the order of the size of the Hubble main mirror. White light interference of the light collected by these separate mirrors enables ultra-precise astrometry. While this would not be a trivial mission to carry out, these parameters show that it is not infeasible, and since obtaining access at sufficient strain sensitivity in this frequency band is exceedingly challenging, it may end up being a promising route to pursue.